Hi, I hope you can hear me.
I can hear you great.
Okay, thank you. So, so let me start my presentation. So, I would like to give a talk about the Python usage in the Belle II experiment. This is the contents of my talk. Firstly, I will briefly introduce the Belle II experiment. Then I will talk the two topics about the Python usage. First one is the Python in the Belle II analysis software framework. Another one is the Python in for workflow management at Belle II. So yes, this is brief explanation of SuperCACB and Belle II. The SuperCACB accelerator is the asymmetric electron and positron collider. And most of data is taken at the center of mass energy, is at the epsilon 4s resonance. Then the BB pairs are produced efficiently. The goal of the luminosity is 3 times 10 to the 35, and integrated luminosity is 15 bar Sato. That is the 50 times higher than the Belle experiment. The Belle II detector is also upgraded from Belle detector with the several improvement. So like particle resolution is improved by introducing new pixel detector. And k-pi separation is also enhanced by newly introduced PID detector. And we have some new trigger line for dedicated for the dark sector search. And so far, Belle II took data that corresponds to the 430 investment one of the total integrated luminosity. And SuperCACB recorded the world highest luminosity, that is 4.7 times 10 to the 34. That is twice higher than the CACB already. And Belle II has already started to produce high quality result with upgraded detector and analysis techniques. So yeah, there are some results from the Belle II experiment. For example, the B2K union in the B2K union search, Belle II has already showed the very competitive result with previous experiment, even with very smaller data size. And the Belle II started the PMS on time-dependent CP violation measurement. That is one of the flagship analysis in Belle II. And Belle II also play an important role for the dark sector search. So this is one of the example of the Z prime to invisible search. So Belle II has set the world-leading result on this field. Okay, yeah, that's about the introduction of Belle II. And here I would like to explain about the Belle II analysis software framework. Yeah, so to provide the public result from the experiment, so we need several steps to do. This is the typical the analysis framework. The flow of at Belle II. So firstly, we have to trigger event and take data with dedicated DAQ system. And its output is stored as raw data, like a detector readout. Then we have to reconstruct a high-level object, like a track or calorimeter clusters. And such an intermediate output is stored as the MDST object. And here MDST is the Belle II jargon. It's a mini data summary table. And then the Belle II analysis is performed. That means using the Belle II dedicated data object and provide the usual particle particle level information. And then finally, we will perform the offline analysis and the measurement to provide the result. And the Belle II analysis software framework is newly designed to deal with all these processes. And it is called PyHEP2022. And indeed, for the offline analysis part, one can choose the dedicated analysis framework by user by own. But the PyHEP2022 also provides some handy tool for the offline analysis. And in my talk, I do not cover this offline analysis part. It can be chosen by each user, but in the following slide, I will a bit more talk about this PyHEP2022 framework. So again, the Belle II software, the PyHEP2022 is completely new, and it's used for everything from triggering data, generation of Monte-Carlo event, tracking, clustering, and high-level analysis. And it is now the open source software since 2021. And the main languages in PyHEP2022 are the root for input and output, C++ for the heavy lifting part, and the Python for steering file. And there are still some large contribution from Fortran, but they are mostly from for the Monte-Carlo event generator. And before moving to the Python usage, I would like to explain a bit more about the PyHEP2022 design. So in the PyHEP2022 analysis, there are three main items. The first one is called the PyHEP2022 module. That is a set of classes that process data. And each module has its own dedicated the purpose. So we combine the several modules to process data. And the second main item is the data store. So that is a set of classes that hold the data and allow module to pass things one to the other. So in the PyHEP2022 design, each module does not communicate directly, but the output of module A is stored in data store, and then it will be used by the other modules. And the last one is the PyHEP2022 path. That is an order in which the module must be executed. So one register the modules in the path with the order which one want. Yes, this is the schematic view of the design of the PyHEP2022 analysis. And here is the typical path for an analysis job. So here we want to process MDST object to produce some particle level information in the T3. So again, that is green box is the module, and the blue is the path, and this gray is the data store. So in this example, so firstly the module to load the MDST is called, then MDST object is stored in data store. Then second module process the MDST object to provide the final state particle list, like electron, pion, and kaon. And using its output, and one can combine the particle to reconstruct the intermediate particle. For example, the B meson is reconstructed from the kaon and the electron pair. And its new particle list will be used in, for example, to do some vertex fitting or calculate some complicated variable, and then do some selection on the particle list. And finally, the one write the information of this selected particle to the T3. So this is the typical possible analysis job. And here I come back the Python usage in PyHEP2. So the main use case of Python in the PyHEP2 is the steering file to arrange the appropriate modules in the path and the configure modules option and the start data processing. And the Python provides a very easy understanding syntax, especially for new users. And the PyHEP2 module can be written in both C++ and Python. In principle, the framework modules are written in compared C++ code, but each user can easily add one own module by Python. And the functionality is exported by Boost Python, and access to the data store is provided with PyRoot. And also, the Python provides a good documentation tool with Python. So using the Sphinx, using Sphinx, the documentation web page is generated very beautifully. So here is the typical the simple steering file using the Python. So firstly, import the PyHEP2 framework, then create a path at first. Then one can add the module in this path, calling the add module function. And in this example, this root input module is called to read this mdsd.root. So using this function, the module is registered in the path. And then one can add more module in the path. Then finally, the process function is called for the path, the given path. The modules are executed for each event with the given order of path. And and in the PyHEP2 framework, there are a lot of the wrapper function, especially for this adding the module part. So there are a lot of wrapper functions for module configuration and adding the module in the path provided with well-documented Sphinx web page. So it's quite small, but in this the modular analysis Python file, there are a lot of the wrapper function to register the module in the path, and this create this the documentation for the documentation in the Sphinx. Okay, this is the main usage of Python in the PyHEP2. But here I would like to add one more thing about the within the PyHEP2 framework. So the MBA package of PyHEP2 provides a tool to integrate the MBA or machine learning method in PyHEP2. So thanks to this module, one can apply the MBA during the this PyHEP2 event routine, and the trained file can be read from the database. And the full event interpretation and the flavor tagger are deployed with this MBA package. And in this package, the default method is the first BDT. And also this package provides a lot of handy tools for training or validation. And but not only this fast BDT, the frameworks that have a Python interface are supported in this package, like a TensorFlow class, XGBoost or something. So yeah, this is due to the easy extensionability of the Python. Okay, then here I'd like to move on the next topic about the Python for workflow management at Belle II. So in high energy physics, some complex workflow have to be managed time effectively and with good reproducibility. So here I put the two examples. The first one is the data calibration. So in the data calibration, there are a lot of interdependent steps to deal with the detector condition that can vary over time. And to provide the result in timely manner, the prompt calibration of data is very important. So in this stage, not just a single bus-to job, but there could be several processes relate each other. And also there are a non-bus-to job, like upload file to the database or open and close Jira ticket or something like that. So yeah, it's very complicated workflow. And another item is for the about the reproducibility of analysis. So yeah, one we want to reproduce analysis procedure for new data or new software version. Okay, thank you. So and in this step, there could be thousands of batch jobs have to be managed. So to deal with such things, the Python plugin packages are developed and used for the workflow management. So I will explain a bit more about these two items. But okay, first one is the calibration strategy, the calibration of Belle II. So there are two strategies in the Belle II and data calibration. This is the prompt calibration. So this happened every couple of weeks for the initial processing. So to do that, Belle II developed the called the B2 cow Python package based on the Apache Airflow to automate the prompt calibration. So as I said, the calibration has a very complex workflow composed of the several processes. So to deal with, we adopt the Airflow, that is the directive acyclic graph workflow manager. So this is one of the graph of the process. As shown, this it's very much complicated to do manually. So yeah, this helps to automate the process, and it also reduces the possibility of human error. And the time taken to perform the prompt calibration is getting decreased as more experience is gained. Okay, and this is the next item about the analysis reproducibility. So in the bus-to analysis, there could be the huge number of batch jobs for segmentalized input data. So for that, we are using the B2 Luigi that is developed based on the Luigi. But it provides some helper functionality with the 1,000 batch jobs. And it is originally developed for Belle II, but it's on the public. So B2 Luigi means both B2 batch to Luigi and the bus to Luigi. And it has the several bus to helper function and the functionality interface to submit the grid jobs. And this can be used each users. But here I put some example of usage of B2 Luigi. This is the systematic correction framework to perform the performance study, especially for the particle identification. So a difference between data and the Monte Carlo on the physics performance is a main source of systematic uncertainty for many physics analysis. So we want to reproduce this study for new data and Monte Carlo several times. Then we developed this framework and developed the library is based on the beta Luigi to reproduce these processes. Okay, so yeah, I do not explain that too much, but yeah, this really helps to reproduce this functionality. Okay, and this is the summary. I do not repeat that too much, but yes, the Python is actually a key language in the Belle II experiment, thanks to the user-friendly interface and the extensibility to many libraries. Okay, yes, that is all from my side. Thank you very much.
Okay, thanks. Thanks for the very nice talk. It looks like we have at least one question. So let's go to Slido. And so Henry asks, why boost Python instead of PyBind 11? Is there already heavy boost usage? I wasn't aware of much that was still using the classic boost Python.
Well, sorry, I am not familiar with PyBind 11, so maybe I cannot answer correctly, but yeah, originally, yeah, boost Python is used from the first development, but it might be another possibility to deal with the connection between Python and C++ module. Yeah, so but I'm afraid I cannot answer the why exactly we are using this framework instead of the PyBind 11. Sorry.
Okay, thanks very much. Let me just let me check Slido to see if we have anything else. It doesn't look like it. Okay, so I think we've finished a little bit early, but thanks again for this very nice talk. And it's always really exciting to try and see how the experiments are using Python at scale. So this was great.